Okay, we'll get started. Right. So I think today what we are going to be starting is to look at the ways of simulating the perpendicular and parallel polarization structures. Okay. We have done only 1D propagation in space for the transmission lines and for the plane waves. Right. So today we are going to start with slightly more complicated polarization setups. That is, we have already seen perpendicular and parallel polarization. So I will be going over the perpendicular polarization in full length from start to finish. For parallel polarization, I hope that you will be able to make a program on your own. Right. So I will begin. Okay. So I will go back to the schematic that we had drawn before. So we had an xz plane, all right, and the y-axis was pointing out of that plane. Electric field was having a component in the y direction, and the magnetic field was having x and z components. Okay. The direction of propagation is in the xz plane. The y direction, there is no propagation. These are the basic things that we are seeing from the oblique incidence on dielectric interfaces, specifically for perpendicular polarization. Okay. So now we are going to take the same thing and we are going to try to arrive at some equations that we can use in Octave to start modeling these concepts. Okay. Before beginning, let's make some small notes over here. All right. So I am having Hx, Ey, Hz. Okay. These are the three components that we have for that particular polarization. Okay. Other than that, the direction of propagation is in xz plane. Okay. This means that your k vector had an x and a z component. Okay. So the other way that we can look at it is when we are talking about the modeling, usually we have to start with the curl equations. Okay. So previously we had done for Ex, Hy, Kz. All right. Now it is a little bit more involved. That's all. Right. So I'll write down the first curl equation that we are going to write in difference form. Okay. Okay. So I have del cross H is equal to epsilon dou E dou T. Okay. So we begin by expanding the left hand side. So I have I, J and K. Okay. Now since the propagation is only in the xz plane, dou by dou x, this becomes 0 and dou by dou z. Okay. There is no ky, so that means that you do not have dou by dou y. Okay. And H is having x and z components, so I will write down Hx 0 Hz. Okay. Now we expand this determinant. Right. So I hat is 0 multiplied with 0. So I have a coefficient of 0 for the I hat. All right. And then I have minus j hat dou Hz dou x minus dou Hx dou z, right, plus k hat times 0. this is my left hand side. So, just to make it easier, I will just remove the 0 terms and I will also take the minus sign here inside. So, that I will have j hat multiplied by dou hx dou z minus dou hz dou x. Okay. So, now that I have a left hand side, I am able to notice that if I use this configuration with hx and hz for a plane of propagation in xz plane, I am getting del cross h to have only a j vector component, which should tell you that the right hand side should have only a j vector component. So, I already know that my right hand side is epsilon dou e dou t, e has only a y component, right. So, that will be its matching, right. So, let us go ahead and write down the right hand side also, right. So, I have epsilon dou e dou t, this becomes epsilon dou e y okay. So, the equation is telling you that LHS is equal to RHS. We can forget about the unit vector in the y direction, alright. We can just equate the coefficients of the unit vector. So, you will have dou hx by dou z minus dou hz by dou x is equal to epsilon dou e y dou t. Okay. Now, having expanded this, we are going to start writing down the finite difference form, alright, and identifying what is the unknown, bringing it to the left hand side. Here we know that we have a quantity with a time derivative. So, it should be abundantly clear that the time derivative means that the unknown quantity for this equation is the value of that variable at the next instant of time. So, you have to use forward difference for time, alright. So, we will start writing this down in the difference form, epsilon dou e y by dou t right. So, I will be having epsilon E y, right. E y is a function of x, z and time, right. So, I am having t plus delta t minus E y of x comma z comma t divided by delta t. Okay. So, the right hand side looks like this in the difference form, the left hand side will have to be written in the difference form. Okay. Okay. So, I have dou hx by dou z to be the first term, okay. So, this becomes hx, it is a function of x, z and time. Okay. So, now I need to make a spatial difference of the magnetic field, right. So, I will simply use say forward difference for one kind, backward difference for the other kind. It is the same thing that we have been doing in the past programs. If you want to avoid problems related to only forward or backward difference, for example, in the prior programs if you switch the order in which you take the difference or if you make both of them to be forward difference etc., you would have had instability issues. If you do not want to deal with them, you can always convert all of them to central difference. But since we already have a base program before, I am just moving on in the same manner. Okay. So, I am going to be having h of hx x z t minus say hx x z minus delta z The other term that we have is dou hz dou x this would be the difference form. So, we have to add, we have to take the left hand side, right hand side, equate, push one unknown quantity to the left side and have all the other quantities to the right side. So, okay. So, in this case I will just write down the expression that we will get. Okay. So, I am having Ey as a function of x and z, and the future value of Ey is going to depend on current value of Ey plus delta t divided by epsilon. Let us see now, right, what we can do. Now, if you look at the denominator for dou hx dou z and dou hz dou x, okay, the first bullet point here has the denominator of delta z and the other one has a denominator of delta x, right, and you need to take a difference between the two quantities. It will become easier if the denominators are identical. Okay. So, this just means that given a xz plane, you will discretize it in such a way that delta x is going to be equal to delta z. So, you will divide the region into a smaller number of squares, alright. So, we can always say let delta z be equal to delta x, okay, and we can make that as some variable called just delta. Okay. So, in our program and in the way we are approaching, delta means both delta x and delta z. Okay. So, then it becomes easier to take some common factors outside. So, I can have delta t divided by epsilon delta, okay, and then I can write down this term inside of that. Okay. So, I have dou hx dou z minus dou hz dou x. So, I can write down the difference form of that here, right. So, I will be having hx of okay. So, for getting the electric field at the next instant of time, I will need to know the present value of the electric field, alright, and magnetic field at different positions at the same instant of time, and then I have to code this expression in the program for managing this particular curl equation. Okay. Now, the other thing that we have to do is go to the other curl equation that we have. Okay. So, we have the other curl equation del cross E is equal to minus del B del T. So, here we are having ideal dielectrics. So, we are not considering the J, okay, or the displacement current in the case of the first curl equation, and here we are just saying del cross E is minus dou B dou T. Okay. So, you could also write this down as minus mu dou H dou T. Once again, we have to expand the left hand side. Dou by dou x, since there is no propagation in the y direction, that becomes 0, and I have 0 E y 0, because electric field has only y component, right. Now, I have to write down the determinant. So, I am having I times 0 minus dou Ey dou z. Okay, minus j times 0 plus k hat times dou Ey dou x. Okay. So, this is what I have for del cross E. Okay. Now, clearly it is it is having two unit vectors, right, I and k, should give you an indication that the right hand side, which is a time derivative, should also have I and k. That means we are talking about hx and hz. So, we are on the correct path. Right. So, once again, right hand side now this can also be written as minus mu dou hx dou t with a unit vector of I hat, right, and then I have minus mu dou hz dou t k hat. Okay. So, h has been divided into hx I plus hz k. Right. Once you do that, the LHS and RHS, all you need to do is you need to take only the unit vector I, equate the coefficients, and then take k vector, equate the coefficients. Okay. So, the first thing you can do is LHS equal to RHS and equating only the I component, right. So, you will have minus dou Ey dou z is equal to minus mu dou hx dou t. Okay, minus dou Ey dou z is equal to minus mu dou hx dou t, right. So, I can always try to figure out what is the unknown over here. I have a time derivative on the right hand side, which means that I have to represent that as a forward time derivative. So, this I will be having at hx, which is a function of x, z and the future. Okay. hx x comma z comma t plus delta t minus hx of x z t, okay, divided by delta t can be written as 1 by mu times delta z, but delta z in our simulation is denoted by simply variable delta, which is going to be equal to delta x or delta z, right, and then we use a difference for the electric field. Right. Okay. Now, the unknown quantity is the first quantity over here. All the remaining terms go to the right side, and that gives you second equation for finding out hx at the future instant. So, the objective is you had some hx, ey, hz. You have to find out the value of each of these components at the next instant of time, all right, provided you have the values of all the other components at the current instant of time. This is the objective. So, you have to find out update equations for all the three quantities that you are interested. So, hx, ey, hz. So, we have done ey. Now, we have hx, the only thing remaining is hz. Okay. So, you can always say equate the left and the right hand side and equating k components, right. You will end up with another equation okay. So, you have dou E by dou x is equal to minus mu dou h z by dou t. It is not very different from the previous equation that we have written, just there is a minus sign coming into the picture, But other than that, it's very clear the unknown quantity is going to be Hz, right, at x, z, t plus delta t. This is the quantity that we are interested in finding. So, this is going to be the current value of Hz at x, z, t. So, I will be having some expression for finding out the electric field derivative with respect to x, all right. That is it, all right. So, now you have 3 equations, each of them is telling you what the future value of that particular component is going to be, right. So, we stop with this, now we go to the program part, all right. We fire up Octave and we try to write this program now, all right, and then we will start fiddling around with the program to understand a few more concepts. Okay. So, I want to start with some dimensions for the space that we are considering. Let us consider that you have 100 units in the x and 100 units in the y. So, it is a square region. You can consider this to be having 100 delta x and 100 delta z, right. So, you can have x dimension is 100. Okay. Okay. So, I have a space which is 100 by 100. I want to start with some total time for which I want to write this program. I will start with some small values to check if my programs work correctly, and then I will improve the program as and when we go. Right. Okay. So, in order to solve the 2 curl equations, there is one additional thing that you will need. You will need to define the position of a source of this electromagnetic wave, all right. In the case of transmission line, we would have used voltage at a specific place was equal to 1 or 2, etc. In the case of this 1D propagation, we would have used a source of electric field at a particular position. Need to have a source. Okay. So, now what I am going to do is I am going to make it a little bit more generic. So, I am going to say the x position of the source. Right. So, I am saying that it will be right in the middle. In future, if I want to change the position of the source, I will alter these variables. That is it. I won't go to the main part of the program, I will just alter these variables. So, here x source corresponds to a single point in the x direction and y source corresponds to a single point in the y direction. So, okay, the way we are writing y is actually the x in our perpendicular polarization diagram, and this axis was z, but I think that visualization is okay. So, we are trying to make a source at a single point, right. So, we have to see what is going to happen and how we can make some inferences from there, and then slowly we will begin to expand to see what is a plane wave and what is a wave front, etc. Right. So, one of the things that we have to do is define some values for permittivity and permeability. Since I do not like to use the absolute values of the permittivity because it is very small, 10 to the negative 12 may get approximated as 0 and I may not get any output at all. So, I like to use only the relative permittivities. In most of the practical scenarios, I see that people use only the refractive index, okay, which is 1 by square root of epsilon r mu r, all right. So, whatever phenomenon you want to model, you can use the vacuum permittivity to be equal to 1, vacuum velocity to be equal to 1, and then for the other material you use the corresponding epsilon r mu r. You may want to say for example, model the change in velocity, change in wavelength, etc. right. So, most of the cases this is sufficient, but if you want to go further and get a real accurate value for the velocity, etc., you may have to use 8.854 10 to the negative 12. all right, and the permeability has to become 4 pi times 10 to the negative 7. Right. I don't like using very small numbers, so I will use only the value 1, right, for vacuum. Correspondingly, what this means is the velocity, right, in vacuum is made as some 1, right. So, whatever velocity we are getting, we can normalize it to the vacuum velocity. Okay. I want to divide the space into a number of delta x and delta z. So, I have a 100 by 100 space. I want to divide it into some smaller regions, and we have called that variable as delta. So, I just want to make it as delta is equal to 1. Now, here there is a catch, okay. Delta t. Previously, when we had done all the simulations, we had also used delta t equal to 1. Okay. We had used delta t equal to 1 in our previous programs. Here we have to be a little bit careful, all right, because delta t equal to 1 can lead to instabilities in the program, all right. I will not go into a large amount of details for this because there is an advanced course for you to take computational electromagnetics, all right. But the premise of the argument is like this. Okay. Suppose I take a few grid points in my space. Suppose I take a few grid points in my space, and let us say that I put a source over here, all right, in this point, and right. Now, at the next instant of time, the idea is it has to go to the next grid point so that you can see the propagation in your simulation, all right. So, what essentially that Maxwell's equation is saying is it will move one grid space in one unit time that you have taken, then only you will be able to see what is going on, all right. So, here our velocity is equal to 1, all right. So, it should go one grid point, right, in one time step. Previously in the case, whatever we have done before in the case of transmission lines or in the case of 1D propagation, the grid points were along a line, okay. So, for this electric field to move to the next point, all you had to do was, you know, model it in such a way that your delta t is 1, delta x is equal to 1, c is equal to 1. So, it will move to the next grid point in one unit time step. Okay. Now, in this case you have a two dimensional space, so a little bit more care has to be taken. Okay. Suppose you have a point source, the point source usually gives off circular wave fronts. Okay. Circular wave fronts. So, if you have a point source of an electromagnetic wave, it is going to give circular wave fronts. Okay. Then you have to think about what all can happen, all right. The electric field can go from here to the next point to the right, it can go to the next point to the left, can go to the point on the top, bottom, etc. But it can also go in these directions, all right, can also go in these directions. Now, how you define the nearest neighbor is a complicated question to ask. Okay. Now, suppose I want this program to remain stable. Okay. The premise is you have to consider this region, all right, because the velocity will be maximum according to the program in this region. Why? Because in one unit time step, you want the wave front to go from here to there to capture this direction propagation. Okay. Otherwise, you will not capture it. In one time step, the wave front, all right, has to go in this direction. It travels a longer distance. So, if your side is going to be marked by A, this is also A, this distance is A root 2. It travels a longer distance at the same delta t. Okay. So, you have to consider the highest velocity in your system possible and then figure out what your delta t would be like, right. So, in this case, we have to consider this to be the maximum velocity because in delta t travels a root 2 distance, but in the other directions, all right, for a time delta t travels a distance only of a. So, in these directions, all right, the Cartesian directions x and y, right, your velocity is only a divided by delta t, but in the diagonal direction it is a root 2 divided by delta t. Those things come into the picture. More details will be given to you in the higher level courses. Okay? And if you are already, you should have a feeling, if you are going to go for a 3-dimensional space, then you have to consider the body diagonal, alright, because the velocity along that will be the highest. So, depending upon the dimensionality of the problem, the choice of delta s and delta t should be taken care of, right, but it is not very difficult. In this case, right, we will define delta t to be equal to, say, delta divided by c, and we have to factor this root 2 somewhere. So, I am going to introduce a factor 1 by square root 2. This is the only catch in this entire program, right, and I will not go into more details about this because this is a topic that is dealt very extensively in the other course, computational electromagnetics, where you will be studying about Courant Friedrich Levi stability factor, alright. But for now, I think this is good enough, right? You have to account for the nearest neighbor, that is all. Okay. Now we can go on with the remaining parts of the program. Hx is now going to be 2-dimensional. It is going to have some zeros in all the space that we are considering, right. Hz is also going to look like zeros everywhere. Ey, starting it off with zeros. Okay. And on top of that, I want to be able to use this program to model dielectric interfaces, just like what we have done in the theoretical parts, which means that when I am talking about a space grid and I want to talk about dielectric interface, I want to have the power in the program to change the permittivity at different places. Okay. So, epsilon, okay, should be actually a matrix. We have put epsilon 0 equal to 1 and mu 0 equal to 1 prior in the program, but what I want to do is I want to create a matrix right. So, what I am doing here is epsilon 0 multiplied by 1s of x dim comma y dim. So, epsilon becomes a matrix with dimension x dim by y dim and it has 1s everywhere. We are starting with pure vacuum. Later on, if I want to change permittivity only on the right half or only on the top, only on the bottom, alright, if I want to create multiple interfaces, I can always manipulate this epsilon. Okay. 1s actually creates a matrix with dimensions x dim y dim with all the elements being equal to 1. Okay. Remember that you cannot put epsilon equal to 0 because 1 by square root epsilon naught mu naught is the velocity, it will become infinite and the whole theory will fail, right. Similarly, you can also have mu is equal to mu naught times x dim comma y dim. Okay. Now, all we are left to do is start to write the loop. So, I am going to have a main loop is there an issue? Okay. This part becomes, is there an issue?
Shouldn't it be x dim and z dim?
Yeah, you can change it to z dim. Originally, I had written it for x and y direction the way I see on the screen, but actually the x in our derivation, this direction was positive z, this direction was positive x. So, you can always change it. It is just a detail. Nothing will change. I think after writing the program, we will do a control F and we can change. Maybe that is easy, right. Okay. So, now I have a time loop and then inside this I need to have some updates for all points in space. Okay. So, I am going to have for I equal to I'll just make it 1 to x dim minus 1 for j equal to 1 to okay, going to take the expressions that we have got in the finite difference form. All we need to do is we need to update magnetic field and then we need to update electric field. So, I will start with magnetic field update. So, I will just say Hx I comma j I will update first, okay, is equal to Hx I comma j plus delta t divided by delta to mu of I comma j So, I am putting j plus 1, okay. Originally in our code it was z plus delta z is equal to 1. So, I am just making j plus 1, right, minus Ey of I comma j. This is what an update equation for Hx would look like, right. It is a lengthy expression, but if you are able to work it out, then there is no issue at all. It is just plugging that expression over here. Right. Then we have to go for Hz of I comma j, Hz of I comma j, and I think in this case there is a minus sign coming into the picture. So, I will just copy paste this part. So, it was forward difference for dou Ey dou x. Right. So, in the first line I have j plus 1 and j, here I have I plus 1 and I, right, that is the only difference of course Hx and Hz. Okay. Now, this loop will update the magnetic field, right, at the current instant of time for all points in the space that we are considering. Right. So, and once we have done that, because the way we have written our prior codes was having forward difference in one part, backward difference in another part, etc., we have to write another space loop, because here you see the, for example, I have dou Ey dou z goes to j plus 1 and j. So, the highest spatial position is j plus 1. So, that is why we are having x dim minus 1 and y dim minus 1, so that you do not go array index out of bounds, alright. But in the other part we will be having a j minus 1 or I minus 1. So, you do not want to go out of bounds. So, you need to write another loop, right. So, I will have for I equal to 2 to x dim, for j equal to 2 to y dim, right, and then I will write down an update equation for Ey. Right. Okay. So, minus Hz of I comma j plus all right. It's a lengthy expression, right? But there are no tricks or anything. I mean, whatever you have written with your derivation is the exact same thing written in the difference form. But those are the tough parts, that's it. I mean, all your update equations are done for Hx, Hz and Ey. Okay. And once you are able to do this, that means that you have written the curl equations accurately. All you need to do is now define the source value, define some plotting commands, and you are done with the program, all right. So, let us go ahead and do that. So, I want to have a source at x source comma y source, and I am just going to make it 1. So, I am going to have a point source of 1 volt per meter at the center of the simulation region, right, and I want to make some plot, all right. So, I will just do image SC. I want to make a plot of Ey first, right. Okay. And I want to give it some title. Okay. The title that I am putting here is the current time instant for which it is solving, so that I can estimate how slow or how fast it is, etc. Right. And I know that if I have this plot commands within the for loop, before it plots, the computer will try to calculate the next arithmetic calculation. So, you need to have a small pause command over here. Okay. So, almost everything is done in this program, and the only thing that we need to now do is run, right. Okay. So, I am going and hitting run, right. Okay. Now, I see that I have a point source at the center. Even though our grid is it's supposed to be a square region, because the monitor is having space in a rectangular manner, it's plotting as a rectangle. So, we'll fix that, right. Also, I don't like the color it's showing. So, I use jet, and I also want it to be between something and something. So, just modifying the image SC command to go between -1 and +1. Small details, that's it. Even if you don't have these parts, it's fine. Once again, axis is 0 to 100 here, 0 to 100 here. Because of the way the image commands are used, we can always use another command axis equal to make it look like a regular graph. So, 10 time steps, I had a point source of electric field, all right, and it is giving out circular wave fronts. Okay. In some of your computers, this may be very slow. Okay. So, we will fix that in the next class to get to a little better option, but for now I will just increase the total amount of time to say 100, right, and I will run this. Okay. Oh God. Okay. We can see that as time progresses, the source is going outward. You are having the electric fields going outward. Since it is a point source, it is giving out a circular wave front, okay, and we are plotting y value of the electric field. The other thing to notice over here is in the center you have a bright red dot. As it goes outwards, it is becoming more and more yellowish, all right. It's because of the color scale, right. Now, one of the thing is the yellow part is actually having less electric field magnitude than the red part. So, it is telling you that as it travels out, the energy is getting distributed across a larger region, and the peak value of the electric field that you are having going out is actually reducing, right. So, now it will hit the boundaries. Okay. Now, we will start some weird, start to see some weird things, right. So, you are having reflections from the boundaries, okay, and clearly we can figure out a few things. The left and the top boundaries are doing something different from the right and the bottom boundaries, okay. There is a pattern, all right. In the left and the top, it looks like the electric field is decreasing, the net electric field is decreasing, something hit, something got reflected, the superposition of the two was becoming green over there again. Actually, if you have the color bar, then it would have become easy to okay. So, I have the color bar. I'll also make the axis xy so that we can, okay, this is easy. Oh God. All right. So, I have left and bottom, okay. So, this is going from 0 to 100 on both sides, which is easier for me to interpret, because when I am writing a code I do not want to see different axes, 0 to 100 on the x, 0 to 100 on this axis. I have a source right in the middle. It was giving out circular wave fronts. The wave hit the boundaries. Some portion of it got reflected everywhere. Almost all portions should have got reflected because we have not handled any boundary condition. By default, we have left it to something. We have to see what is going on, all right. Here and here looks like something is happening that is different from the top and the right hand side, right. So, clearly this is the effect of boundaries, and I can guess that in this place the electric field is flipping its direction upon reflection and then adding up to the one that is going and hitting the boundary. So, it is creating some negative or destructive interference, right, and you are having a net 0 electric field coming into the picture. Here maybe it is not changing its sign. So, I can guess what kind of boundary conditions I have. If the electric field is flipping its direction, means that you have a perfect electric conductor. So, I can guess that I have a perfect electric conductor on the left and on the bottom, and I have a perfect magnetic conductor on the right and on the top, because the electric field did not flip. If I plot Hx Hz, I will be able to figure out what is going on with the other two boundaries. So, I get a rough idea. Just like in the case of transmission lines, you had open circuit in one side, short circuit on the other side, etc. All right. Here it is the same thing that is happening. Now, since you have a base program, there are a variety of things that one can do. I can manipulate the source. I can say that let the source be, say, a sinusoid of frequency, say n by 4, or time period I am changing. Okay. So, with respect to time, it is producing a positive electric field and a negative electric field. Positive electric field corresponds to, say, red color, negative one corresponds to the blue color, and as it goes out, you will see that the color is fading a little bit because the energy is getting distributed throughout the wave front. Okay. when it was starting, the wavefront was so small, the energy was only in a small place. As it goes out, the energy is getting distributed everywhere, so it becomes lesser and lesser intense. Then it hits the boundaries, and then you start seeing strange things happening. Okay. Now, this is perpendicular polarization. The only thing that is different here compared to what we had done in the class is we had plane waves with a clear direction of travel. All right. Here we are talking about wave fronts that are circular. All right. So, one will have to fix it. In order to fix it, there are some ways. Right. Either you can make your simulation region really large and wait for the circular wavefront to look like a plane wavefront at some faraway place. All right. Or you could start manipulating the source. For example, I could say that just okay. So, what I have done here is instead of having a single point, okay, I am having x source minus 25 to x source plus 25. That means that I am going to have a line which is going to be emitting an electric field corresponding to sin n over 4. So, when I run this, you will be able to figure out exactly what I have done. So, if I want to create a plane wavefront, all I did was take a series of point sources at different places along the line and then made them all emit with the same phase. That is it. So, I am getting a line shaped wavefront coming to the sides, okay, right. But still I am having something going out here, right. It is a natural consequence, you cannot do anything about it. So, now we have the base program for perpendicular polarization to be ready, right. Now, there are a few things that we have to do more, right. First, we have to see if we can make this program a little bit faster so that we can run a lot more experiments. Okay. So, we already know how to do that. We can vectorize the for loops. So, in the next class, we will vectorize the for loops, make it a little bit faster. We will see the comparison one to one, and then we will start playing with material interfaces, all right. And then we will see whether whatever we have got in our analytical results, are we able to make some additional visualizations over here and draw some more inferences. Okay. So, we are going to put some interfaces and start to see what is happening, right. So, this is how one would simulate Maxwell's equations in 2 dimensions, and this is the limit to which we can see in this course, because 3 dimensions the computer will become really slow. Okay. So, we will stop here, we will meet in the next class, which is tomorrow. Please bring your computer again, and we will be making a faster version of this, and we will be putting interfaces and trying to draw inferences. Okay. And for parallel polarization, after we have gone through this whole exercise, my belief is that you should be able to write your own program. All it needs is changing the update equations. That's about it. So, I will stop here.